Good evening, ma'am.
Hi. So, Agilan, you have seen previous lectures?
No, ma'am. I saw the lecture notes, but have you recorded the lectures, ma'am?
I have like a bits and parts of it because there was some connectivity issue at my end. So the like one of the lectures kept dropping, and the other time, out of four lectures, there is problem with two of the lectures.
Okay,
But
ma'am.
whatever pieces I have, I'll try to sort of amalgamate the videos and put them on YouTube and provide the link.
Yeah, okay, ma'am.
Okay. So, did you guys see I've uploaded an assignment on the Moodle?
Yes, ma'am.
Any issues, any questions, queries? Saham,
Yes.
any doubts with the
Um,
hmm? So, did you guys go through the exercises given at the end of chapter 1 of generating functional logic group?
um, sorry, ma'am.
Did you guys go through the questions?
Yes, ma'am. I
Exercise.
went through. Ma'am, I went.
Hmm?
Ma'am, I went through the questions. It's okay. Ma'am, can we do it in LaTeX and submit the PDF, or does it need to be handwritten?
If you do it in LaTeX and submit, that is the best because then I do not have
Okay.
to really boggle my mind around your handwriting. Okay. So that way, submitting it through the like PDF which is generated by LaTeX is best.
Okay.
But if you feel that it's taking up a lot of time and you're not like ready well in time, then probably it's okay. You can submit the handwritten notes. But since I'm taking the submissions through Moodle, you'll have to make sure that your file is short enough even after the scanning of pages. It's for the people who would plan to. Okay, so as I see, there are two people who are there in my course, formally registered, right?
We use in the limit, I guess.
Sorry?
Like we can split the files if it's large.
No. Since assignments I'm not really giving as group assignments. Oh, you're saying your original file itself will
Yeah,
submit as parts.
yes, yes. Yeah. Like if the size is a problem, we
Mhm.
can just split the PDF into two pieces and send it.
Oh, okay. I wasn't aware that Moodle allows multiple submissions from one participant.
Yes, ma'am. It does. Like I
Okay,
did
then
it.
that's great.
Yeah.
So that solves one of the problems. Another thing is, so I will grade them and then let you know the feedback through the feedback section, or I'll annotate the PDF itself directly into the Moodle so you'll be able to see. Fine.
Okay.
So, Ridhiman and Agilan, since both of you are MSc students, if I'm not wrong, is that right?
Yes,
I'm
I'm an MSc student.
it's,
I could not hear. Agilan, you are MSc second year. Ridhiman, you? Ridhiman?
Yes, I'm MSc Computer Science.
Okay, so then I can actually expect both of you to know LaTeX and submit it through LaTeX.
Yes, ma'am, I can do that.
okay, ma'am.
Same for Agilan. So please, both of you submit it. I mean, take up your solutions, and it's always a good practice to write the question in the PDF file itself as well. Okay, so
Yeah.
your assignment sheet would look like you put the question, and then you give the solution.
Yes, ma'am.
Okay, so that it's like nicely arranged, and I don't have to go back to see the questions separately. Just I can see your solution sheet and I would know what I'm looking at. Fine.
Okay, ma'am.
Yes, fine.
That is some standard instruction. And as I have already told in the assignment sheet also, wherever you take the clues from, hints, suggestions, discussions, whatever, you're supposed to give due credits. Okay. Anything which is taught in this course by me does not need a credit. Everything else does. Understood?
Yes,
Yes.
And I am really strict about this. If I find any two of you providing me with the same sort of solutions, and there are no credits given to each other or to the main source of information, I would penalize you. I will be generous most of the times, but with the credits I will be harsh. So if you take any information from anywhere else, be it Google, be it any friend, be it any senior, junior, professor, colleagues, doesn't matter. You have to give them credit. Okay? You can do it question wise, you can do it at the beginning, you can do it at the end of your assignment sheet. Is that fine?
Yes, ma'am.
Take this particular instruction very, very seriously. And the second part, every step should be clear enough, because I really do not want that I would grade and then when you see the remarks and you'll come and say, ma'am, I meant so and so, I just did not write it. If you do not write, I do not give marks. As simple as that. I will give you marks only for what I see. Okay? Okay?
okay.
Okay, ma'am.
Okay. Another thing which I needed to talk about is that next week we will not have any lecture. So the two lectures which are supposed to happen in the next week, those two lectures I will arrange by taking the other lectures little longer. Okay.
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 And this, so since both of you, okay, so Agilan is new. Agilan, am I pronouncing your name right?
Yes, ma'am. Agilan. Yes.
Agilan. Okay.
Yes.
So Agilan, do you mind if the slots stretch a little? Like instead of
Yeah.
5 to 6:15, if it goes on till 6:45 or maybe 7 also sometimes?
Yeah, it's fine, ma'am. No problem.
Okay, great. So this week we'll have the usual timings, today and day after tomorrow. Next week there is no lecture, and the week afterwards the lectures will be elongated to take care of the missing lectures. Either I'll compensate within a week or perhaps 2 weeks. Okay.
Okay, ma'am.
depending on how we see and like where there is a good time to stop the lecture. Okay, so that being said, let's start. There is something. I don't know. Sure, no problem. So even if you're leaving the lecture, it is not really a problem with me. The course
Okay,
material
ma'am.
will anyways be available online in the Moodle, and I have started recording the lectures. So like the previous recordings also I have, not sure how good or bad they are, because people who have attended, they know the last meeting dropped like hell number of times. And once when we met for a longer time, and that day it was not a usual standard time, so I did not have license. So we had to do the lecture in 3 meetings of 45 minutes. So that way it is little bad, but yeah, it's okay. I'll upload whatever I have, and from now on we have all the recordings. Okay. So Rishikesh, you can leave when it's time for you to.
Yeah.
No issues with me.
Okay.
Okay, so let's start the lecture. And you're supposed to tell me if something is not clear and all, etc. Okay, because I may not be able to read your mind completely. Fine. Okay. So let's start. This is one, let's try. So in the last lecture, if you guys remember, we talked about the manipulations of these formal power series, right? We talked about various operations which we can do on these power series. Okay, so since Agilan is new, uh, since we are very few students in this class, we keep ourselves all unmuted so that we can actually have an interactive session rather than, me just teaching and you being just a listener or watching some TV somewhere. Alright. So today we will see what other operations are possible in this ring of formal power series. So in one of the old lectures, you might remember that we dealt with two types of power series. One was ordinary formal power series, and another was exponential formal power series. Right? So today we are going to attack different operations here. Yeah. Okay. So just as a notation, if I write fx to be summation en xn for n greater than equal to 0, this in shorthand I will write this as that f is ordinary power series for the generating function en. Okay. So this is going to be the standard notation. Fine. Now, can we do some manipulations? If let's say I know that this corresponds to this, what really be an plus 1 0 to infinity? First of all, this in terms of this particular notation, what does this mean? This is summation en plus 1 xn n greater than equal to 0. Is that right? Which can now be rewritten as summation en plus 1 xn plus 1 divided by x n greater than equal to 1. Is that right? Sorry, not this way.
Isn't it still 0?
Yeah. Not even 0. If I'm raising power 1 and I'm starting from 0 here, the first term is a1x0, right? So here a1x1 would come. So x0 I have to sort of banish. So I should write this as which then is same as an xn but n from 1. Is this fine? Yeah.
Yes.
Now this is same as, so if I had written this to be starting from 0 and subtracting this term which I added, which is a0, x raised to 0 is 1, and now this you know is what? This is, yes please. This is correct. So in the notation that we have, what we really get is that an plus 1 corresponds to the form of power series which is given by this function. Is that right? See, since I'm very good at making mistakes, you have to keep working these things out with me and make sure that there is no mistake happening in these mathematical calculations, arithmetics and all. Okay, just how I did a starting from 1 here and then that would have messed up the entire calculation. You have to stay with me and be cautious of what we are really doing. What happens if I try to do this? What would this be? Any guesses? Yeah. Yes, somebody at least. Riddhiman. Okay, let's start doing it and then we'll see what really happens. So summation an plus 2 x raised to n starting from 0 is what we have to find out. Now this, again the same trick we'll do. Summation a n plus 2 x n plus 2. I have taken a x square in the denominator outside and starting from 0, right? And now again the same thing, very much the same thing. So since plus 2 is there, the summation really starts from 2. And this is a n x n, correct? Whereas this now can be rewritten as f of x minus, what terms did I had to really add here to make it fx? A0 and
A1.
a1x, correct? So what we get from here is that this entire thing translates into fx minus a0 minus a1x whole divided by x square, correct?
Yes.
And was there any smarter way to do this? Hmm? Yeah. Another way how you could have, so at least this much we know that n plus 2 really corresponds to the ordinary power series for the function fx minus a naught minus a1x divided by x square. Okay, so this much we know. The way how we could have tried finding it is that n plus 2 summation xn n from 0 to infinity, instead of doing all the way till where we did, we just do it till here, right? And this is what? Summation n plus 1 xn n from 1, right?
Yes, sir.
Now, do you see a pattern? Can we really compare this along with what we did here? There is just a shift of 1, right? N equal to 1 is the only shift. So this is really 1 by x summation if n started from 0, an plus 1 xn minus, what did I add here?
Yes.
A0. Okay, and this corresponds to x0. No, I added a1 here. You see, n equal to 1 gives me an plus 1. So a2 x1 is the first term here. Whereas this actually corresponds to, seeing the previous formula, this, right? An plus 1.
Yeah, right.
So I substitute that back here to get f, not f0, I'm sorry. So see how good I am at making these mistakes. So you have to be really careful. F minus a0 by x, and this minus a1 stays. So this all together now is f minus a0 minus a1x over x square. Do the answers match?
Yes.
Yeah. Is this and this term same?
Yes.
Great. So no matter how we arrive, either we do the brute force method, which is this, you take it all the way down to n equal to 0 and add, subtract, do the manipulation which anybody would do who doesn't know this, or you can be smart enough to use what you have computed earlier like this and arrive at something like this. Okay? So in short, what I have achieved is again. Okay. Now, quickly, can someone tell me what will be an plus 3's ordinary power series generating function?
Fx minus a naught minus a1x minus a2x squared by x cubed.
Others do agree with Ridhiman?
Yes, ma'am. Yeah.
Okay.
Yes, ma'am.
So with this, so others as in people who are not okay with this, please sit down and verify this later after the class. But this brings me to the rule number 1 for the formal power series generating functions. And that says that if fx is the ordinary power series generating function corresponding to this, then for any positive h, an plus h corresponds to, yes please,
Fx minus sigma a, okay, like that, till uh, a1x, a2x squared dot an x to the n,
you sure?
h x to the n. Oh, right. X to the power a.
Correct?
Yes.
Okay, fine. So this being the rule number 1, what is the next thing you would want to really see? Like here we did a shift in the subscript of an, right? From an we saw what would be the ordinary power series generating function corresponding to an plus 1. So this has rule number 1 has taken care of all these shifts in the subscripts of a, right? That is it.
Ma'am, I don't know if the
That's
problem is from my end, but at times your voice is breaking. So the last what you said, it wasn't audible. Is the problem for everyone, or is it for me? If the others can con.
Yeah, I also couldn't hear the last 3-4 seconds.
Oh,
Yeah,
then
yeah.
possibly this is my issue. So what I said is, with rule number 1, we saw what happens when we do a change of subscript in the coefficient of x raised to n, right? So when we shifted by 1, this is the change that we encountered. When we shifted by any h or any positive k, this is the change which we will see. Now we see what would happen if there was some natural number coming along with an. Okay, so here is a question. So if En corresponds to F, so instead of writing Fx, I would just write F, okay? Then what is NAN corresponding to? Yeah. Well, what do? We have seen this in past. So anybody ready to speak up?
You differentiate, I guess.
Yeah. And so let's start seeing what happens here. This is what we have to compute. Correct?
Yes.
So on the side, we try to see what will happen if I take the derivative of this. What is this going to be? Yes. Yes, people, please. So derivative also I have to write, huh?
N x power n minus 1.
So this is going to be summation n x power n minus 1. Correct? Correct?
Yeah.
But now we are actually in short of one particular x. This looks pretty much like this particular one. Even this term here is pretty much same as this. If you go and compare these two, the power of x is different, right? So that is what we need to manipulate here. How do we manipulate this? Quite easy for us. Is that fine? So this is nothing but x d dx of summation n xn. Correct?
Yeah.
Yes.
So the symbol d dx, we will let's just use something nice. So this symbol we are going to, where is my pen? Yeah, seems like there is actually issue on my side. So this symbol we call as capital D. Okay. So putting all this together, what we now know is that xt of f is the ordinary power series generating function that corresponds to n en, right?
Yes.
Yes.
Okay, so this was about an an. Can we do any better? Like, can we proceed further in this? What would happen? Next question is, what would be n square an? Yeah. So one way is we can sit down and do this entire calculation again, or we can try to really mimic what we did to arrive at a n plus 2's corresponding ordinary power series generating function for a n plus 2 in the terms of a n plus 1 and hence in the terms of a n. So let's try to be smarter, and then this really boils down to the answer that n square a n 0 to infinity actually corresponds to x dx of n a, which is actually x dx of f. Isn't this?
Yes.
So this is nothing but xt square of f. Okay. So everybody understands when I write this, it's like you take the derivative and then multiply by x. Yeah, remember this notation which we have done here? So this d is this d and this x is outside this d. So first you differentiate this entire thing which is inside the bracket, then you multiply the resultant item with x, and so xd square, which is xd, you do this here, which means you do d of f, then you multiply the answer with x, and then you take a d of that, and then you multiply with x.
Ma'am, you are not audible.
Hello?
Yes, but your voice broke down.
Sorry. So xt square of f, when we write here, this really means that you take d of this f, then you multiply the answer with x, then you take d of that, and then you multiply that answer with x. That is what this entire entity is. Okay?
Yes.
So with this, can anyone tell me what this would be? What color code was this? Pink. Okay. So if an corresponds to f, then for any k in n, n raised to k a n 0 to infinity corresponds to,
Xt to the power k times f.
that's right, xt operator applied k times to the formal power series f. Okay. Okay.
Yes, sir.
So let's do an example. Let's compute this. So let's say we want to compute what happens for the generating function given with the recurrence a n plus 1 an plus 1 is equal to 3 an plus 1 with the conditions n greater than or equal to 0 and a0 is 1. Okay. So this is something about the change in the shifting in the subscript of an, okay, along with the product, right? Yeah. Am I audible?
Yes, ma'am.
Yeah, but I'm not hearing anybody's voice, so I don't know.
Hello.
I don't need the hello. I asked questions. So if this is the
Yes, ma'am. I actually replied, but I don't think you heard.
oh, I didn't hear it then. Sorry. Yeah, please tell me.
Can you repeat your question?
The question is using what we have learned, using the rule 1 and rule 2. Okay, so rule 1 talks about shift in the subscript of A, and rule 2 talks about multiplying an with n raised to k. So in such a scenario, what do we do? Using these two rules, if I multiply this entire equation with x raised to n,
with
and
coefficients being an, right? And then do like xd into f equals 3f plus 1 by 1 minus x, I think. And then, well, I'm missing one term somewhere. You have to correct that also.
yeah, so please tell me this.
Yeah, so for the left side, it's xd into f, or I don't know if it's into whatever that operator is called.
Yeah,
xdf equals 3f plus 1 by 1 minus x, I think.
okay. And have you taken care of the
I haven't.
subscripts here?
I think I'm missing some term, probably like a 0 term or something.
So let's just see. Let's just see for a second that NAN would have given XD raised to K, right?
Yes.
So if I was working with NEN, so first of all, let's just so let F correspond to the formal power series which has coefficients an. Okay. Then the things that I know is that I know are an plus 1 would have corresponded to f minus a0 over x. Since a0 is 1, this would be f minus 1 by x. And the second thing that I know is that an would have corresponded to xt of f, right? So first question is, what does this correspond to? There is a shift here, and then there is a multiplication with the same subscript.
Like, can we split this into n times an plus 1 plus an plus 1?
Sure, you can,
I think
but
we just subtract the A1 term.
Like,
you don't know what a1 is.
like if we split this, we'll get n times an plus 1. That first term will be xd of f minus a0 by x, right?
No, you're mistaken here. See, this k is in n, which means you have, I mean, here you cannot have a smaller value,
Yeah.
right? So an plus 1, what happens, you don't know. What you're suggesting is this, that we do an plus 1. But what this corresponds to?
Well, I think we divide by x actually, because what you get when you do the xd thing is like a1 x plus 2a2 x squared and so on. But what we want to shift by 1. So you divide by x and you have what you need.
Okay, can you show this to us? You can
Yeah.
share your screen and show.
I don't think I'll be able to draw.
You can use the whiteboard which is provided by Zoom.
1 second. You disabled participant screen sharing. So I'm saying instead of xd, it should just be d.
Why does it always show that way? Have any idea from where can I start showing? Okay, are you able to share now?
Yeah, now I can.
Yeah. So we both should be able to share right now.
Yeah. So we have like f. Sorry, this is a bit hard to draw, but
Others are able to see his screen?
I can't see
Yes.
this.
no.
I can see.
So should I pin them? Like,
Even I'm
On
not able
whiteboard
to
right
see
now.
his screen.
So actually, there's an option to select which screen you want to see on the top. So from there, we select his screen.
I am seeing only my screen. It's okay. I'll stop my screen and then we can see what he's sharing. Yeah, now I can see.
yeah, I
his
can
screen.
see. Yeah.
I have only a trackpad, so this stuff.
Yeah, that
So
is fine.
we do df equals a1 plus whatever 2a2x this equals sum for n greater than or equal to 0 of n plus 1 an plus 1, sorry, x power n. So we have what we are looking for from just differentiating without multiplying by x. And then on the right side, we just do 3f equals and then we also need a 1. So we do like another thing, which is add x plus, sorry, 1 plus x plus x squared and so on. So in the end, what we get is this is our left hand side, right? So we have df equals 3f plus the ones which are embedded into this infinite polynomial, which is 1 by 1 minus x. And so this is a differential equation, which is like linear or something. I don't remember how to solve this, but it's well known, I think, how to solve it. I can't tell if I'm making sense.
Yeah, you perfectly make sense. Let me just straighten out what you have said. And is my screen visible now? Is my screen visible? Is my screen visible?
Yes, Bharat.
I can't actually see your screen.
Oh, you can't?
Yeah, now.
Oh,
Yeah, now.
so what he said is that this summation is nothing but the df. Okay, if you simply apply d by dx on summation an xn, then you get this. Okay, so this takes care of the left hand side. Now coming to the right hand side, which was 3an plus 1. When you do x raised to n multiplication here, what you get is 3an x raised to n plus x raised to n, and then you do summation starting from 0, right? So this is the embedded term which he was talking about. This everyone knows now is you just take the 3 out, and this inside thing is f, and this is nothing but 1 upon 1 minus x. This we have done earlier also. Remember, everybody? Series, so
Yes.
expansion for 1 upon 1 minus x is actually 1 plus x square and so on, which is precisely this. Okay. So the generating function for the recurrence equation given by this n greater than equal to 0, a0 equal to 1 is nothing but f prime equals 3f. Excuse me, 1
You
upon
wrote
1
the-
minus x.
You wrote the first thing wrong.
Where?
The first line, it's n plus 1 into an plus 1.
Oh, yeah, right. Absolutely right. Thanks. So I'm giving you more and more reasons to trust my words that I will make mistakes like this. Okay, so now this is a ordinary differential equation of degree 1. This can be solved using whatever ways you have in your pocket. So you see how easily we have shifted ourselves from something which looked so tedious to solve to something which is just an ordinary differential equation. That is the power of generating functions. Maybe I'll say this like 10 more times since this is the course we are dealing with. Okay. Now, putting this aside, let us now come back to the modified rule 2. So, modified rule 2 will say, what was correct? Rule 2 prime instead. So this is a generalization of 2. That's why 2 prime. And what we say here is f is the ordinary power series generating function that corresponds to the coefficients an. Excuse me, I'm so sorry. And p is a polynomial. Everyone understands what a polynomial is, right?
Yes.
Then when you multiply the polynomials with an, so polynomial in n, right? So you remember, right? We did the shifting business and we did the multiplications by n sort of things. Correct? So then this will actually correspond to, any guesses? We have already done this. Okay, let's just do some homework. If it was a 3an, it would be, so first of all, even let's say break it down even further. Any polynomial will have constants and or powers of n, right? Is that right?
Yes.
Am I audible?
Yes.
Yeah.
So if for an, what I have is f, for any fixed integer alpha, alpha en will correspond to alpha f. Alpha is constant.
What? What's alpha?
Constant.
Okay.
Because you can simply just take that out of your summation and
Yeah.
then whatever is left inside is just f, right?
Yeah.
We saw what happened to n raised to k an. This gave rise to xt applied k times to the power series f, right?
Yeah.
Also, if an corresponded to some f and some bn corresponded to g, and you do an plus bn, what will this correspond to?
F plus G, I guess.
Great. Same thing, you would do x raised to n multiplication to this entire thing, take the summation, then summation just distributes over this summand, and then you'll have summation anxn plus summation bnxn. Summation anxn would be f, Summation b and xn will be g, right? So with all of this in our pocket, now can you answer this? Okay, let's break it even further. So if I have, let's say 3an plus 2bn, what will this correspond to?
3f plus 2g.
3f plus 2g. Everyone fine with this?
Yes, ma'am.
Instead, if I had a 3an plus nbn, what will this correspond to?
3f plus xdg.
Plus xdg. Great. Now, if I had some n square an plus nbn, what will this correspond to? Yeah. Guys, quickly. Individual terms you have to just see.
XD square F plus
Thank you. Xd
X-
square of f plus
XDG.
xd of g. Great. Now, if bn is also same as an, what really this is? So this would correspond to
XD square plus XD of F.
everyone with me so far till this step?
Yes, ma'am.
Yes.
If the polynomial function px, or don't say x, you will get confused, no? Let's say pz looks like z square plus z, what can I write this to be? Can this be written as pn?
Yes.
Yeah. And which, so this side will be, if I want to write it in terms of this, how will this look like? What should I fill in here? Is this right?
For every x power n in Pn, just replace that by xd and yeah, right.
Yeah, fine. So with all this computation, now coming back to this, if Pn is the polynomial that gets multiplied with An, this corresponds to what? Now you should be able to tell me quickly. Pn is nothing but a polynomial in n, which is here.
Yeah. P of xd into
P of xt applied to f. End of the story. Okay. So this takes care of the all powers of n which could possibly come with an and even the additions of such terms. Right?
Yeah.
So everyone is actually convinced as we are actually dealing with the generalization of rule 2.
I have a more general question, which is
Yeah.
that like it must be really difficult to like compute them and solve them if xd appears more than once, right?
Yeah, it would be, but like hopefully, see, XD would appear more than once only when you are dealing with terms where you have higher powers of n involved in the generating in the recurrence relation, right?
Yeah.
So applying XD to a polynomial is not that hard. But imagine about trying to do that otherwise. So for instance, what I'm really saying is that xt being an operator, let's say even k times, if you apply it on a polynomial of degree less than equal to k, you're very sure what answer is going to be.
Yeah.
Right? I mean, not very sure also, because there is this x term which gets
Yeah.
multiplied after every differentiation. So the degree doesn't really come down, but still it is doable since it's going to be a polynomial. But if it was any function just like that, and you would want to solve that using the generating functions which we had done in the chapter 1 of this book, it would have been bizarre to really come down to the calculations. It would be messy. We are not really saying that you have to do something like n raised to 10 en. Computing this, not easy, but hopefully doable. And this is the hope.
Yeah.
Okay.
Yeah.
So yeah, this is the rule 2. Now let's see if we can solve another example. So we have to find this n equal to 0, n squared plus 4n plus 6 upon n factorial. This is what you have to compute. This is equal to what? Okay, so if I just follow blindly what I did in the earlier section, oh, so it's 6, 8. You guys don't mind if we stretch it by 15 or 10 minutes?
No problem.
I don't have any problem.
So till 6:30 we can go, right?
Yeah.
Yeah, ma'am.
Okay, great. So, okay. So this particular thing, if let's say the polynomial in n, I take this to be n squared plus 4n plus 6. Okay. Everyone understands what 1 upon n factorial corresponds to?
E power x.
E raised to x. We have done in earlier lectures, right? This is going to correspond to e raised to x. So this entire thing along with the rule 2 will correspond to, if I have like multiplied the entire equation by x raised to n and then summing from n 0 to infinity, what I'm going to get? I'm going to get xt squared plus 4 times xt plus 6 at e raised to x. This is what this will translate into. If I had multiplied the entire thing by x raised to n and then summed over this, and then later I'll evaluate it at x equal to 1, then this is the thing which I would be computing.
Yeah.
Right? So I am till here now. This, you say, okay, this is xt of e raised to x is, sorry, d of e raised to x is Derivative of e raised to x
itself.
itself. And then you have this x from the first operator. So what you are actually having is x ex. Correct? So this first term evaluates to this plus 4 times x ex, right? Plus 6ex. Is that fine? Now xd of this. So derivative of this is x ex, keeping x constant, e raised to x comes to e raised to x. Then differentiating x and keeping this constant, you get e raised to x plus 4x e raised to x plus 6 e raised to x. This then is equals to x squared e raised to x plus 1 times e raised to x and 4 times e raised to x. So 5 times x e raised to x plus 6 e raised to x. And now, so this entire thing being evaluated at x equal to 1, right? To arrive at this, correct? Correct, students.
Yes.
So now I am free of all the operators now. So this at x equal to 1 is nothing but e plus 5e plus 6e equals 12e. Is this correct?
Yes.
Everyone?
Yes.
So this entire thing was legitimate. We did not do any mistake. So 12e is indeed the answer to this particular equation. Yeah.
No, but like, if you like substitute E, the series for E, that won't look like this, right?
It will have this product, no?
Yeah, but what about the numerator?
Numerator along that is coming as a function of n here.
No, no, like you mean the answer, the 12E is the summation, right? That is what we have concluded. Is it?
Yeah. Even if that is a problem, I say there is some bigger problem than that. Can somebody help me?
Yeah, is it convergence?
Even let's say suppose this n factorial wasn't there. Whatever we did, was that okay?
I don't think it could be convergence because factorial grows like even faster than exponential, and it seems like it should be fine.
So what we did is fine.
I don't see any problems.
Okay, others. Okay, so what really was the way to come around for this particular answer? That we identified something in here and we replaced that entire thing with whatever knowledge we had, and we said that, oh, if this is what we compute and evaluate this at x equal to 1, we'll get the answer to this. Is this really an equation that we deal with here? No. Formal power series, these are formal series, these are not actual series, right? You cannot really evaluate them at any particular number which you wish. because it does not exist. So we
Mhm.
like took the generating function which corresponds to this, and then we said, oh, if you evaluate that at x equal to 1, this is really the number. But you don't evaluate your formal power series at any given value. These formal power series, if you remember in the first lecture, we said this is just a representation which takes care of the coefficients. So x raised to n is actually a formal variable. It's just a variable. You can't substitute values there because it does not make sense. For all these things to make sense, you will then have to care about analytically what really happens to this as a series and not a formal power series. So this is really just for the representation purpose. So it's not possible to evaluate such formal series at any given values. If we analytically analyze them and figure out that, oh, at so and so x is equal to alpha naught, so and so power series as a power series, not as a formal power series. So there is a huge difference here. That's why we keep, pressing the point that these are formal power series. These are not normal general power series. These are formal power series. There is a formality. This x is not something which can be substituted for any value. These are just variables which are existing there to take care of the coefficients a subscript n. There is no meaning to x raised to n other than this in these formal power series. So if as a power series they converge in some particular disk, then for any point in that particular disk, you can evaluate these power series. But all that analysis happens analytically, okay, not as a formal power series. Yeah.
Yes, ma'am.
But nevertheless, what we know is that if we could analyze them, if there was analytical answer to the fact that, oh, so and so power series is going to converge in so and so region, then we could have evaluated the series at a given point. In fact, at any point in that particular region where it is converging. Okay, but otherwise it's not possible. So this entire thing, what we did is actually cheating. So this is a huge no. As fx is a formal power series and not a power series. So evaluating fx at an x equal to x naught is not legitimate without analytical analysis of this fx as a power series. Okay, so everyone agrees with me till here?
Yes, ma'am.
Great. Now let's come to an example and then we'll quickly see 2-3 more rules and then we'll stop. So example is this. So you have to compute the sum of so sum of the squares of first n naturals. Okay. This is the task at hand. This, I claim, is doable by looking at this. So, how is this term really going to help us? This term. First of all, everyone knows that this summation is nothing but x raised to n plus 1 minus 1 over x minus 1. Okay. Now, let's just try to write down few terms of this thing. So let's say n equal to 3. What is this going to tell me? This is
Wait,
x plus x. So it starts with 1, right? X raised to 0, x raised to 1, x raised to 2, plus x raised to 3. If you apply derivative on this, what is this going to be? 1 plus 2x plus 3x squared. Is that right?
Yes.
So xt of xt of this thing is going to be x plus 2x squared plus 3x cubed. Is that right? Just multiply x in this. Fine.
Yes.
And then I do xt of x plus 2x squared plus 3x cubed. What is this going to be? Now d of x is 1. D of 2x squared is 2 square x plus 3 square x squared. So this is again x plus 2 square x squared plus 3 square x cubed, right? if you really had one more term here, so if you had an x4 and let's say one x5 also, and you applied this operator twice, what would this be? Yes, people?
You get till 5 square x power 5.
Sorry?
X plus 2 square x square up to 5 square x power 5.
So you really see what is happening? This is n square x raised to n. N coming from 0 to, what is this? Whatever is the last, let's say n. Correct? So this is what you're trying to find out. Sum of first and natural numbers. Okay. So this is what we do now. To find the summation n square of first and natural numbers, this is nothing but the operator applied twice to the summation we gave upstairs, which was this. Okay. So let's just this. Okay. So we get xt twice applied to x raised to n plus 1 minus 1 over x minus 1. You do all this calculation, and in the end you should actually arrive at n plus 1 to n plus 1 divided by, everyone remembers this formula
6.
from the childhood, sweet memories. So verify this. Okay, this being done, let's quickly come to the next rule. So earlier when we were trying to do the rule that talked about the polynomials, we already saw what summation of two formal power series gives rise to, right?
Yeah.
Now we see the product. So if f corresponds to an, g corresponds to bn, then as one would expect, fg would correspond to an b n minus r summation r from 0 to n and this. So now each term of this particular series, formal power series, is going to have this as the coefficient of x raised to n. Yeah, don't forget the notations. So this really
AR,
means,
B, and minus R.
yeah,
Is it AR, B, and minus R?
oh yes, thank you. Thank you. Thank you. So this is almost obvious. Yeah. In the same line, we see the next rule. Which says, so here you have seen the product of two, like in this same line, you could have even had FGH, okay, assuming that H corresponds to some Cn. Then this FGH would correspond to what? Summation AR, summation BS, I mean summation of AR, BS, CT, where these individual indices add up to n, and then n going from 0 to infinity, right? So for any finite, so rule 3 can be generalized to a product of finitely many formal power series. Okay. Now, in this, if I keep all the formal power series to be f itself, what I get, or rather, what we simply have is given the name of a new rule. Since I'm trying to follow the book so that later, if you see the book or you see the notes, you don't have a confusion. That's why sticking to the book, if f is the ordinary power series genetic function that corresponds to an, then for, okay, this is f, any k positive natural number, positive integer, fk will correspond to, yes please, summation an1, an2, how many? Such that the summation ni is n, and n ranges from 0 to infinity. Okay? Okay.
Yes, ma'am.
Are we connected? Okay, so if I use, so using rule 3, can someone tell me what would be, what would this correspond to?
Summation AR,
Summation AR
x bar n minus r.
x कहाँ से आया अंदर? So summation AR then R in this form.
Then x bar n minus r, right?
See, there can't be an x powers inside the brackets, right? These are just the coefficients that are.
Oh yeah, it's all one, right? Sorry. Just
Yeah.
r from 0 to n.
R from 0 to
N.
n. And then n goes from 0 to infinity. Everyone agrees with this?
Yes.
Because 1 upon 1 minus x has the power series expansion summation x raised to n. Right? Okay. So since I don't hear a lot of yeses, this is nothing but summation x raised to n. And n greater than equal to 0. Okay. So this is my gx, and gx corresponds to bn. I know that my bi's are 1 for all I, right? And so if f corresponds to an from 0 to infinity, f product g will correspond to summation ar bn minus r going from 0 to n and 0 to infinity. But each bi we know is 1. So you replace this entire thing. So this is replaced by 1. Therefore, this is nothing but the summation ar are ranging from 0 to n. And this is what we get. Okay?
Yes, ma'am.
So this is actually the real file. F is the ordinary power series generating function corresponding to this, then f over 1 minus x. This corresponds to summation ar r from 0 to n. Okay?
Yes, ma'am.
So this we end here. Straight line. So this we end here. And in the next lecture, see analogous tools for the exponential generating functions. Right? So all these rules that we saw today for the ordinary formal power series generating functions, we will see next time for the exponential power series generating functions. If you are not sure of what exponential type of generating functions are, please look back to, I think, lecture 3. Okay, there at the towards the end you will find the exponential generating functions. Okay, thank you people. So today we end here.
Thank you, ma'am.
Thank you, ma'am.
Okay, so we'll meet day after tomorrow And again, it will be a little stretched meeting because, as I told, next week we won't be meeting. Okay, but the assignment is due Monday night.
Okay.
Yeah?
Yeah.
Okay, thanks. Bye.